a little bit larger than what was before, right? This is okay. Okay. All right. Okay. So, thank you, Kaushik, for the invitation. I've had a fantastic time here. Of course, this is I spent a lot of time in the Western Labs. I don't know if you guys know, at the corner of Western Labs, I don't know whether that corner still exists. That's where I spent many an afternoon polishing samples as a metallurgist. He said it is material science and engineering. At the time, it used to be called materials and metallurgical engineering. Actually, when I joined, it was called metallurgy. Then it became materials and metallurgical engineering, and now it is material science and engineering. But anyway, I had a fantastic time here, so it's always a pleasure to come back to this place. So today I'm going to talk about quantum theory of materials, methods and applications, and I have tried to keep the talk fairly general. For the experts, I apologize in advance, but I hope for the students it is somewhat useful. If not, I apologize in advance again. So here's the outline. I will talk about the quantum theory of materials and methods that we use for calculating material properties. This is where I'll spend bulk of the time. Maybe half of the talk will be just an introductory talk about how do we calculate electronic structure properties of materials. And then I will spend a little bit of time talking about double excitation in materials and why they're interesting, and then talk a little bit some technical stuff about what we've been up to recently. Okay. So, as you all know, the basic idea of a lot of condensed matter physics and a lot of material science is to understand properties of materials from their structure and composition, right? And typically we will do, I mean, I'm a theorist, so typically what we do, all of this is by using theory to actually go from structure and composition to properties. But of course, what we would like to do is to have a very detailed microscopic understanding of the properties of the materials, not just a phenomenological understanding, but we would like to understand, in a sort of from a microscopic study, we would like to understand these relationships. And perhaps more importantly, we would also like to be able to predict and interpret experiments, right, that are done on these materials by many of our colleagues who do experiments. And experiments can be on the structural properties, dynamical properties, electronic properties and optical properties of these materials. And of course, what one would like to do ideally is not just go from here to here, but rather have a set of properties which we want in a material and go back and close this loop, right? And that's sort of the holy grail and sort of the inverse problem of saying that given a property, can you tell me a material which will actually satisfy this, which will have these properties. And so this is the big picture idea of what quantum theory of materials is all about. It's usually given a structure and composition, can you predict the properties? Now there are many kinds of ways in which one can predict properties of materials, and the kind of methods that I'm going to be using are called first principle methods. So what are first principles methods? They basically are methods where there are no adjustable parameters in the theory. Okay. Now that does not mean that there are no approximations, right? I mean, of course there are approximations, right? But approximations are well justified and tested. And the reason why we want to use these methods to understand these properties is because if you have no adjustable methods, adjustable parameters, and your methods are reliable and sort of well justified and tested approximations, in principle you can use them to predict new properties of materials where you actually don't know what is going to happen, where there hasn't been an experiment that has been done on that material. Yeah. There is of course a con to everything. There are two sides of a coin. So the con here is that these methods are typically computationally very expensive. So this is sort of this is the advantages and the disadvantages, and this is sort of the advantages of using first principles methods. As a result, there are only, you cannot explain all kinds of phenomena. You cannot do systems which are typically extremely large in size, and you cannot construct, for example, the kinds of things that a metallurgist would see in a grain boundary in a very large system. Those are not the phenomenology that you will try to understand using this. But nevertheless, some band structure kind of properties are the kinds of properties that you can understand with this kind of methods. Okay. So what are the kinds of properties that we are talking about? What are the kinds of properties that one can use to understand using these first principle methods? These would be properties which are structural properties, and everybody in this room has probably gone to this X-ray crystallography, has done this course on X-ray crystallography, or at least has done some X-ray crystallography in the lab. And you measure lattice parameters. You can also have things where you have simple phase transitions of the kind where you have, let's say, going from one phase to another phase of a material using pressure. So those kinds of things you can explain using these methods. You can calculate structure factors, pair correlation functions. Of course, these are just Fourier transforms of one another. Elastic constants. These are the structural properties that we would like to be able to understand. There are dynamical properties, things like lattice polarizabilities, Born effective charges, heat capacity, infrared spectra, which experimentalists routinely measure, right? Raman spectra. So these are the kind of dynamical properties that we can understand using ab initio or first principles methods. Electronic properties like conductivity, density of states, which can also be measured using photo emission spectra and the like. And I'll spend a little bit of time on these optical properties, things like reflectivity, absorption, refractive index, everything that is related to the dielectric function, right? Those are the kinds of properties that these methods can try to you can try to explain these things using ab initio methods. Okay, so the thing that is common amongst all these methods is that these all depend on the electronic structure of the material, right? So what we would like to do is we would like to be able to calculate this electronic structure of the material. Okay, that's a simple problem, right? After all, we all know how to write the Schrodinger equation down for a solid, so off we go, right? You write the Schrodinger equation down for a solid, H psi, Z psi, time independent Schrodinger equation. H is the Hamiltonian, T is the kinetic energy of the electrons, kinetic energy of the nuclei, U is the electron energy, this is the electron ion, and this is the nuclear energy and the electron ion energy, and there's any external potential. Done, right? We've written the equation down, we can solve it, off we go. Except before we solve it, let's just think about how many variables are there in this equation, and you realize this is a hopeless task, right? This equation contains 3 times n, Z times n plus 3n, where n is the number of electrons in the system, atoms in the system, and Z is the atomic number. Typical solid, Avogadro number of atoms, and you start thinking to yourself, wait, this is the number of variables we are talking about, not the number of, this is the number of, this is the order of the psi this is the number of variables in psi. So clearly this is an impossible task, right? So what is the solution? The solution is we stop all of this and go home, right? No. So we have to figure out how one can go about solving this equation, and it turns out there's actually a very famous saying from Paul Dirac. This is something that he realized in, this is 1929, right about the time when all of this was written down, in the Schrodinger equation and all was written down right at that time. This is in this paper he says, the fundamental laws necessary for the mathematical treatment for a large part of physics and the whole of chemistry are thus completely known. He's talking about when you've written down the Schrodinger equation for the solid, right? And the difficulty lies only in the fact that the application of these laws leads to equations that are too complex to be solved, right? So people often say this and say that this is very complicated, but actually even in 1929, in the next paragraph, the starting of the next paragraph, this was the ending of the paragraph, in the next paragraph he says, it therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, right? And so that's what we're going to talk about, and this is what we call as are these ab initio methods. So the first approximation that comes to mind is what is known as the Born-Oppenheimer approximation, right? So the idea is the following. We know that electrons move fast while nuclei are slow. I'm saying this as a colloquium speaker in a very sort of qualitative sense. You can make this mathematically a little bit more rigorous, and in the way that I'm saying that's sort of related to the ratio of the masses to some power. So if electrons move fast, namely that they readjust instantaneously, of course nothing is instantaneous, but we assume that it adjusts instantaneously to the position of all the atoms, then of the ions, then what you can do is you can write the wave function, the wave function which was dependent on the position of all the electrons and all the nuclei, you can actually write it in this form, where this is just the electronic part of the wave function, and this is the nuclear part of the wave function. And essentially what you're trying to say is that I'm not going to worry about the nuclei. The nuclei are fixed as far as my calculation is concerned, and they give me an effective potential in which the electrons move. And if I move the nuclei, I find a new potential in which the electron, this is the new potential in which the electrons move. Okay? This is called the Born-Oppenheimer approximation. So this gets you somewhere because you have removed this a large fraction of this factor of z, right? I mean, because you have removed you have removed the one factor of n in that in that equation, right? Not the one that you care about, but anyway, there's still a very large number of degrees of freedom because all the electrons are there in the problem. So then you start asking yourself the following question, right? You know from elementary chemistry that this is drilled in right from the get-go. Valence electrons are all that matters for determining chemistry. That's not entirely true. I mean, there are some cases, if you do XPS experiments or something else where you're actually probing the core electrons, then of course it's a different matter altogether. But in a large part of things that you do, it's only the valence electrons that play an important role in determining the properties of a material. So if valence electrons are the only ones that matter, why exactly are we carrying all the electrons in the calculation? Because after all, we should be able to remove all the rest of the electrons, and they shouldn't make any difference whatsoever to any of the properties that I calculate. So this idea is basically captured in this idea of a pseudopotential, where you say that look, eventually the core electrons are all static, they don't do anything. So maybe I can write, if I ask you for the potential for an atom, you will all say it is minus z over r, right? Z is the atomic number, right? But if I say, okay, now why don't I remove all the core electrons and only keep the valence electrons in my calculation, you have to now come up with a new potential. And so it's called a pseudo potential, right? For the lack of a better word, right? And the pseudo potential essentially captures the physical content of the periodic table, right? Some people may disagree, but by and large that is the idea, that all the core electrons should be removed from the calculation and we should only worry about the valence electrons in the calculation. Yeah? How does one go about doing that? So this is a very simple idea, which is that if you think about the the valence electrons, right? You say, okay, look, what is the potential that they see? One of the things that happens is that the valence wave functions have to be orthogonal to the core wave functions. So in some sense, they get pushed out of this core region. The valence electrons get pushed out of this core region because of the fact that they have to be orthogonal to all the states below them, right? And that essentially leads to some kind of a repulsive potential at the core, so that your potential is no longer minus z over r. I've written 1 over r here, but minus z over r. But rather it sort of becomes a different potential, which beyond a certain radius will remain exactly as what it was, which is 1 over r, right? But inside the core, because of the fact that they are getting pushed out, right, you can, if you were to write a potential just for the valence states, they sort of have a repulsive potential. That's the basic idea of what the pseudopotential is. Okay? So that seems okay-ish. I can see some people struggling, okay, maybe we can buy that argument. Even if you buy that argument, you're still left with an Avogadro number of electrons. I mean, this reduced the factor of z, I took out some nuclear degrees of freedom, everything is fine, but I'm still left with the Avogadro number of electrons that I have to deal with, right? And that's where this idea of density functional theory comes in, right? So the idea of density functional theory is that essentially it's a method which tells you the ground state properties of materials, right? Now this is, of course, is a theory. So what are ground state properties, first of all? So this is a theory which describes the ground state properties. These are properties that are intrinsic to a system with all its electrons in equilibrium. I don't mean they're static, but on an average they are in equilibrium, right? They're not they're moving around. Of course, electrons are not static inside a solid, but I can talk about the distributions of electrons. In fact, what density functional theory said is that the total energy of the system, and this is a theory for which actually Walter Cohen won the Nobel Prize, right, in chemistry, right? But what it says is that the total energy is a unique functional of the electronic charge density. Okay, there is, you have these very large number of degrees of freedom. you're going to now, so think about it for a second, right? We had this, we talk about wave functions, right? We talk about wave functions, we talk about this many body wave function, which has, Avogadro number of variables that I still have to deal with. What this theory is saying is that you can write the entire thing in terms of just the electronic charge density, right? This is a remarkable statement. In fact, you have probably India's leading expert in this area in the department. Manoj Harbola he has been given, actually, in fact, for students who want to learn about this, there's 11 lectures that he has given, which are on YouTube, which really are very, you can, if you want to learn this stuff, that's the place to start. Yeah. Essentially, what this theory does is there's a formulation for this theory called the Kohn-Sham formulation, and in this formulation what you do is you map this interacting many electron problem to non-interacting electrons moving in a self-consistent field. Okay, so I had this many body problem with very large number of degrees of freedom, and I have mapped it to solving just this problem, one electron problem, right? I took care of this by taking care of many electrons by removing the core electrons. I threw all the parametric dependence out. All the ionic dependence out. It only comes in through the just the electron ion description, and it's parametric in the position of the ions. And the rest of it is all I need to solve. But I need to solve this equation self-consistently. You recognize the ionic potential, which comes from the pseudopotential. There's a Hartree term, which is just the classical electron-electron repulsion, standard stuff, electrostatics. And then there is this term which is called exchange correlation, right? Which is where you shove in all the stuff that you don't understand, right? And the hope is that you can make a very nice approximation for it. And if you can, right, then you can actually solve this problem easily. Yeah. So, in fact, it turns out, the reason why this theory is extremely successful is because you can actually approximate this extremely well, right? And there are very standard approximations that you can make, and with this you can actually solve this equation. Now, if you realize, if you think about it, this is the wave function. This is the one electron wave function, if you wish, the Kohn-Sham orbitals. Using this you can construct a density, which also goes into the Hartree potential, because the Hartree potential depends on the density, right? So the density is calculated by solving this equation, and then you have to do this, go back, and this is where the self-consistency part of this thing comes in. Okay. Okay. So you do all of this, and you spend all the time, and you put all this together, and you say, okay, now, what do I get? If I do all of this, what are the kinds of properties that I can get? You can get things like, you can predict the lattice parameters of, I think this is silicon. Right? So you can predict what would be the lattice parameter for silicon, right? You can predict, if I take silicon and I apply pressure, it goes from the diamond phase to this beta tin phase, and at what pressure, which comes from this very simple idea of the slope of these curves, will tell you at what pressure will the transition happen. You can predict, even by doing perturbation theory on top of this density functional perturbation theory, you can predict phonons. And then you can also predict, if you want, you can actually also predict the charge density, which can also be measured. I mean, X-ray diffraction, if you put in the structure factors, you should be able to back out the charge densities as well. So this is what you get if you do all of this. At this point, I want to make a plug for a code that we've written. There's a code. I mean, there are many codes which actually do density functional theory calculations. We have a new code which we have written, which does density functional theory calculations, and the idea is that we wrote this code purely in Python. Most codes that do density functional theory are hundreds of thousands of lines of Fortran, 100k, 200k, 300, 500k kind of lines of Fortran. This code is only 8,100 lines of Python, right? It gives you exactly the same answer as many of the standard codes that you use. So if you want to learn about density functional theory, how it is applied in materials, it's a good place to start fiddling around with stuff over here, because this is very simple. 8,000 lines of code is manageable, and you can try to figure out how everything is being done here. Yeah, it also does many other things. I'm not going to worry about that right now, but it does many other things, and it's freely available through this website. Yeah, yeah, yeah. In principle, yes. That was one of the, that was not the reason why we thought of Python. Now it has become extremely relevant. Yeah, absolutely. It's hard to interface. That's absolutely right. That's absolutely right. Yeah, it is. Yeah. That's what you're saying is true. What you're saying is true. Oh, actually, I didn't say here. You'd think it's written in Python. It will be so slow that it won't be worthwhile, right? Actually, it turns out it's only 10% slower than the fast Fortran codes. So you're not sacrificing on speed when you look at this code. Yeah, just a plug. Okay, let's get back to get back to physics again. Okay, what I'm going to spend most of my time talking about. This was about ground state properties, as I said, right? What I'm going to spend most of my time talking about is excited state properties. So what do I mean by excited state properties? So excited state properties are spectroscopic properties that involve experiments that create an excited particle above the ground state. So for example, you take, this is the standard Fermi C, right, without any labels, right, circle filled Fermi C, and then you add another particle to the system, right, or you take a standard Fermi C and you kick an electron out of the system, right. This process is inherently an excited state process, and let me try to motivate why this is an excited state process, because the idea that you need to describe this is actually you need to describe this using this interacting particle Green's function. Okay, why do I pick the interacting particle Green's function? How does that contain this information? So let me just try to motivate how it contains this information. So what is the Green's function? So Green's function is written formally in this way, where these are is the exact n electron ground state, and this is the time ordering operator, and this are the Heisenberg creation and annihilation operators for an electron at a given point. Essentially, what this is the probability amplitude that an electron which is created at r prime t prime, right, will go to RT. That's essentially what this probability amplitude is, right? And this information, this actually contains the information about the excited states of the system. So how does one see that? If you take this object, right, and you just Fourier transform this, right, and introduce completion of states by and do some algebraic manipulations, you immediately see that the poles of this object contain this energy difference. This energy difference is the energy difference between a system containing n particles and n plus 1 particles. So if you think about it, when I started by saying I added a particle and I want to find out what is the quasi-particle energy of this, how much energy do I need to add this particle, right? This is exactly that energy. This is exactly that energy, right? So clearly the Green's function, the single particle Green's function, contains this information that I really want to do. So what I want to do then is I want to calculate the poles of this single particle Green's function, because the poles of this single particle Green's function contain the information that I want, which is about what happens when I add a particle or take a particle out of the system. Okay. So how does one go about calculating the poles of the single particle Green's function? So it turns out, just like for density functional theory, the standard model for ground state properties was density functional theory. The standard model for excited states is Green's functions, and the way you do this is by solving the Dyson equation, right? So you write down the Dyson equation. I have also written the Dyson equation for the Kohn-Sham states. So I had given this equation, the Kohn-Sham equation. I have just written it in a Green's function form, so that it looks a little bit like what the Dyson equation for this quasi-particles looks like. And essentially, if you can transform this under some approximations into exactly these equations, this is the one I had shown you before. So they look similar, except instead of this exchange correlation functional, now I have this self energy, right? So all my interactions, so basically I added this particle, it was talking to the rest of the system. All of that information is now hidden inside this. This object is no longer, this is non-local, right? and energy dependent now. So I need a way in which this can be calculated, right? So, you know, now I moved a little bit forward, but now I need what is the self energy now. So the question then becomes, what is the self energy that we are trying to calculate? So it turns out, right about the time when Kohn-Sham equations were developed, this was done in 1964. In 1965, there was this very nice paper by Lars Hedin, right, where he came up with a formulation of how you can calculate this, approximate this self energy, such that you can calculate these quasi-particles. I want to point out something which is remarkable. I mean, I have never seen this in a paper, but just if I don't know whether you can all see, but this is what he says in the last line of the paper, right? This is a paper, this is in PRB, it was cited maybe 7,000, 8,000 times, I don't, you know, very large number of times. He says, there is not much new in principle in this paper, right? Besides the proof of Luttinger-Ward Klein function variation principle and self-consistent idea, there is not much new in principle in this paper. That's what he says in the abstract, right? The emphasis is on development of a numerically manageable scheme. This is remarkable. I mean, I'm not that brave, right? I really am not, but I just find it remarkable that, you know, this is a paper which turns out to be the linchpin for many of the excited state calculations that we do, and this is what it says in the abstract. Anyway, so Lars Hedin. So I think this was probably the last review paper he wrote before he passed away, and essentially what he said is basically, this is he basically summarized the idea. And the idea is very clearly summarized here. So this is called the GW approximation. So you make the approximation for the self energy in terms of GW. And the idea is you already know what Hartree-Fock is. I mean, everybody knows what Hartree-Fock is, right? Essentially what he's saying is that if you take Hartree-Fock's self energy, which is IGV, you know, we write Hartree-Fock in terms of an outer product of wave functions divided by r minus r prime and so on. You can also write it in terms of the Green's function, right? Or the density matrix in this case, but you can also write it in terms of the Green's function. You can also write the GW, which is exactly similar, except the V is replaced by the W, right? Not because UVW, V W, that's not the reason. The reason is that what you're doing is, this was the bare Coulomb interaction, right? What you're doing is you're replacing this bare Coulomb interaction, which is 1 over r minus r prime, by an interaction which is more relevant inside a solid, which would be the dynamically screened potential, right? So you say that, look, inside a solid, if I'm inside a solid, two electrons don't talk to each other with 1 over r minus r prime. There's all these other electrons which are also there, which are screening this interaction, and therefore what I will do, and this interaction is going to be time dependent as well. So what I will do is I'll replace this with a dynamically screened potential, which is called the W. So of course now the question becomes, how do I calculate this W? Right, what do I do with this W? I know what to do with the G, but what do I do with the W? So this is where you have to make some approximations for the W. I mean, he gave an exact theory which is formally exact. It just gives you the same gives you all the diagrams per the Wick's theorem, and everything is formally exact. Formally exact is very good, but not very useful, because you want to make an approximation because you want to be able to do something. So in that sense, what it turns out is you can replace this W by the random phase approximation W, which is very easy to calculate, and it turns out that this is the first in the series of diagrams, and this is sufficient to explain a lot of the physics that one sees. Okay, so this is what is called as the GW approximation. So now we have the GW approximation. It should also be time dependent, I'm sorry, but the idea is now we've gone from so we have a scheme now. We know the Green's function, right? Let's say we do the Kohn-Sham problem, the ground state problem. We construct the Green's function. We construct the W from this ground state Kohn-Sham states. Construct this operator, and then go about solving this problem, and we should get quasi-particle energies, right? So all sounds good in principle. Does it work? Well, I wouldn't be here talking about this if it didn't, right? So imagine you said, you know what, this is all too complicated. Let's not do all of this. You already had a one electron problem. It gave me eigenvalues. Maybe that's good enough. If you take a large number of materials, right, and you plot the experimental band gap versus the theoretical band gap, right, and you do this within this local density approximation, this Kohn-Sham thing that I told you, this is what you would get. These are the points you would get. And you would see that, you know, this is where it would be if everything were agreeing, experiment were agreeing with theory. Clearly, this is not agreeing very well, right? If you do the GW approximation, this is what happens, right? So now, all of a sudden, we are doing a lot better than before, and we have a, you know, we have a manageable scheme. This is computationally tractable. We can do this on a routine basis, and we have a way in which we can actually try to explain experiments where you add or take an electron out of the system. Experiments like photoemission or inverse photoemission, or places where, you know, change in the electron number is something that would show up. Okay? Okay, so this sounds pretty good. Yeah. RPA. Huh. That's correct. That's correct. Do we take from Kohn-Sham? Yeah. So correct. In principle, you are supposed to solve this self-consistently, right? Which nobody does because it's expensive enough. So typically, you take it from Kohn-Sham, and it turns out that it is reasonably well. In some sense, it's okay because Kohn-Sham, you know, epsilon inverse has some connection to the ground state properties. In some sense, the polarizability should be, you know, you should be able to get them from. There is a starting point dependence because we are not doing self-consistency, which we should do. But it turns out G naught W naught, that means G from best G best W approximation. That means you take a G from LDA or from the best G that you can construct, and W from a different, that works pretty well. You know, this is all done with a one shot. This is not done self-consistently. Self-consistently, it is somewhat sensitive if you are worried about the last digit, last details. For example, if you did consistency, it turns out it overestimates this slightly. But, you know, if you stop at the first one, you get the right answer, right? Not a very satisfactory way of doing things, but that is what people have found, that, you know, it's very expensive anyway. You want to stop at the first one anyway, so you say, okay, I'll stop here, right? Yeah. Yes. No, so this one is so far just the quasi-particle gap. This should be comparable to the quasi-particle gap. So the gap that we are talking about is photoemission and inverse photoemission, the difference between the two. Yeah. If you wish, the Mott gap, or, you know, ionization potential minus electron affinity. Yeah. That's the Mott gap. Yeah. Or transport gap, if you wish. Yeah. Nice question. This is the next thing. Yeah. So the next question then becomes is, you know, that's not the only experiment that we do. The simplest experiment that we do is we shine light on a material and we measure the optical spectrum, right? UV vis optical spectrum of a material. This is routinely measured in the lab. You know, you talked about, you know, adding and subtracting an electron. That's not what is being done when you shine light on a material. You create an electron and hole together at the same time, right? Oops.
So the self-interaction that is typically present in like typical calculus.
Yeah.
Doesn't matter whether whose function we take.
Yeah.
That is completely like.
It's not completely eliminated. That's a very good, interesting question. So it is not completely eliminated. It turns out that this is not completely self-interaction free, and there is some self-interaction in the W that still remains. It is largely eliminated, but it's not completely eliminated. And people claim that this is a problem, and it may be a problem in certain cases, but most of the self-interaction error is actually gone in this case.
So if you take W0, which is on-spot.
Yeah.
Or if you take, you know, consistently update it.
Yes.
Does it correct that error?
It doesn't correct the error. What it does is, you know, so the thing is, it screens it less because the gap opens up, right? So the screens it less, and so the gap opens up a little bit further. It's not a runaway process, so it doesn't go. That's the reason why people stop at the first iteration. But if you do it self-consistently, you'll get the same answer no matter which one problem you start from, but it'll be slightly overestimated from the.
So if you, let's say, start from HSC, which
already
has some corrections of self-interaction.
Yeah.
So then it should give much better.
In principle, but, you know, the question becomes whether the vertex, which is what you've removed from here, how important does the vertex correction become? And vertex correction will depend on what you have built into the G and the W, right? Because every time you're doing a different G and a different W, right? It's an effective G and an effective W. So the vertex becomes somewhat important in the case of HSC. Yeah?
So what works best generally?
LDA, PB, the simplest thing is works the best.
So PB plus
Correct. G0W0 works.
Like LDA is what I use.
Yeah, LDA or PB is also is perfectly well. Yeah? Okay. So now the question becomes, most experiments in the lab, well, many experiments in the, I mean, people do angle resolved photo emission as well, but there's many experiments where you shine light and you look at optical absorption, and so we would like to be able to explain this. Now there are now two ways in which you can do this. One is time dependent density functional theory. That's an exact theory which should in principle be able to calculate this exactly, and there's no problem that should you should be able to exactly be able to tell what the answer is. The only issue is that we don't know VXC very well, and now we want its time dependent, we have some dependence on the time as well, and that makes life a little bit more complicated than there are not as good approximations for the ground as we had for the ground state. So what I'm going to be talking about is what is called the Bethe-Salpeter equation. So the idea is the following. So imagine I shine light on a material. So when I shine light on the material, I create an electron and a hole. I create a quasi-electron and a quasi-hole, right? I don't worry about the fact that, I think of it as, okay, I kicked an electron out, I kicked a hole, I kicked this electron out and I just brought this back into the valence band at this stage, and these don't talk to each other. I just say that they don't talk to each other. Of course, it's not true, right? But I just say that they don't talk to each other, and I can calculate the optical spectrum in that case. It's a very simple Fermi's golden rule kind of an approximation that I can make to calculate the optical spectrum. The real thing is, of course, I know that the electron and hole, if I think of them as a +1 and a -1 charge, right? And I just said that inside a solid they should talk to each other with the screen Coulomb interaction. So these should be there should be an attractive interaction between them, right? So it's like a positronium system, right? That people do in high energy physics, right? The positronium problem. So that is actually involves me, mixing these many electron and hole states, and essentially I shine light and there is some thing that happens, and then I have an electron and a hole inside the system, both of which are present, right? And this is what my real state of the system is, and this is what I should be using to calculate the optical spectrum. Except now what I am supposed to do is not just one electron hole pair, but really I have to look at I have to minimize, I have to construct this correlated electron hole state, right? And this is what was done by Bethe and Salpeter in the context of something completely different in high energy physics, but the same formulation applies here as well. So again, the idea is that we are essentially going to think of the state of the system that we are now constructing as I have a ground state, I create an electron and I create a hole, but now I am allowing them to talk to each other, right? And I have to now find out what these amplitudes are. And once I find this is like an envelope function if you wish, and this is going to give me my entire electron hole.
So, Manish, they may contain bound states, like as you said.
They do. In fact, they do. That is exactly right. In many materials, they actually contain strongly bound states. In 2D materials, I will show you that they're very strongly bound. Right? Depending on the screening. The lower the screening, the better it is. So lower I go in dimensionality, the stronger the binding, the electron hole binding, and they form bound states inside the spectrum.
But somewhere the lifetime should matter, right?
So
all of these positroniums are like stable.
Correct.
What scale you are measuring?
So that's a very good point. So here we are assuming that these are long-lived, quasi-particles are long-lived. These are usually at the band edges, so we assume they are very, very long-lived. So we are now saying that, okay, of course there's a recombination lifetime, right? The whole thing can recombine and light can come out. So I'm assuming that process is not happening. Before that process happens, what is it that I will get?
But the optical properties which you are measuring has to have a time scale smaller than the light.
So absorption, when you normally do, you basically, you can actually, the lifetime doesn't matter all that much. In principle, it can. I mean, it depends on what kind of an experiment that you're doing. But in many of the cases, the lifetime doesn't matter. So then, this is okay. Yeah. Okay. So you have to now solve the Bethe-Salpeter equation for two particle Green's functions, and you can write the electron hole interaction kernel in terms of Feynman diagrams, in terms of this is exchange diagram, and this is the screen Coulomb interaction. Again, you are basically saying that look, an electron and a hole have, they are inside my solid, and basically they are going to talk to each other by the screen Coulomb interaction, but this is attractive. Yeah, and that's going to mix up a whole bunch of things. So you can write this electron hole interaction kernel, and you can solve for the optical spectrum after that.
So what another question?
Yeah.
See, this, whenever you talk about Green's functions,
Yeah,
their poles are very important.
that's what.
Whether you have discrete poles or continuous poles.
That's correct. That's correct.
You,
In this case, we are mostly looking at the bound state, so they are discrete, right? But even in the continuum, it turns out it's okay. This works out very well. I'll show you the result for this. So, for example, if you look at the optical spectrum for silicon, right, about the most studied material on this planet, and the cleanest one as well, I suppose, you can see that this is the experiment, and these are many experiments which I've put together into a single plot. And you say, okay, forget electron hole interaction, let's just do the standard shine light and let the electron hole not talk to each other. This is what the spectrum you will get. Now, it's not terrible, but it's not fantastic either, right? You are missing out on this peak completely, and this one is all in the wrong place. You put in the electron hole interaction, this is what you get, right? Now all of a sudden you have a way in which you can calculate this property, and it is extremely predictive, right? I have not made any assumptions about I have not made any, there are no adjustable parameters in this entire theory. Yeah, so that's the basic idea.
So how do you explain what's the reason behind these two peaks?
So the two peaks are related to this. So there are some. So this is basically, these are excitons which are forming in the system, and so at this energy, the excitons were supposed to be the large density of states of excitons which were formed because of the electron hole binding, which you were missing completely in the other case. And when you do this, there are certain parts of the Brillouin zone where you can actually show that this is where it comes from. The density of states from this part, you do this, you will actually find that this is what the electron hole interaction is attractive. Therefore, this peak sort of moves to the left, and you get this entire very nice spectrum. It's easier to explain when you go to 2D materials, because there were states which were not there before at all start showing up, as he's pointed out. The bound states start showing up, which were not there before. So it's much easier to explain in that way. In this entire thing, the density of states doesn't change very much, but now this particular state, this exciton, has a large oscillator strength as well. So this is epsilon 2, right? I have a velocity matrix element. I'm talking about from the ground state to this state, what the transition, right? That ground state to this state transition is determined by some dipole matrix element, right? That dipole matrix element for the individual transitions was very small, but when I formed the exciton, this particular state had a very large oscillator strength, and suddenly it starts showing up in the spectrum, right? There's some modulation of the density of states as well. In the bound states, it starts showing up places where there was no density of states before, but that is basically the idea. Yeah?
So is there any reason why those bound states are more common or abundant in 2D systems compared to 3D?
Yeah, there is actually. So it turns out screening is usually very weak in 2D systems, right? So if you think about it, what would be the attractive interaction between the electron and hole? If there were no screening, it would be minus E square over R, right? So if I put an epsilon, it is minus E square over epsilon R. So as I go to lower and lower dimensions, it becomes even more strongly bound. I mean, 1D systems have even stronger binding, right? It can be, I will show you for WSE2, this thing can be pretty large. The binding can be very large. Yeah? Okay? All right. So I'm done with the introductory part of the thing. Now let me get to the double excitations. I mean, I had planned for this to be about half the talk. I think maybe I went a little bit over, but it's okay. Okay. So why are double excitations in the materials? Why are they interesting? So it turns out that multiparticle excitations such as tryons, biexcitons are prominent in 2D materials. So let me give you an example. So this is the normal photoluminescent spectra for a 2D material which is WSE2, tungsten diselenide, right? Single layer, monolayer of tungsten diselenide, right? And you notice the band to band transition, if you didn't do anything, the quasi particle gap is more than 2 electron volts, about 2.5, 2.3, 2.4 electron volts, right? This is not supposed to be here. There's nothing here. This wasn't supposed to be here, right? But you have a very rich spectrum over here. And in fact, something very interesting happens when you shine, if you increase the, you're doing this photoluminescence, right? That means you shine light and you wait for what light comes out, right? If you increase the laser intensity, right, which is given by, I don't think anybody can read this, this is watt per centimeter cube, you increase the laser intensity, you start seeing some peaks are increasing in intensity, right? And that's a bit weird because, what does that mean? I mean, you always assume everything is in a linear regime, but there's something quite non-linear that is happening about this in the spectrum. So by the way, as I pointed out, all of these peaks are excitons. These are all bound states. These are not there in the quasi-particle band structure, right? This is well below the quasi-particle band gap. This is not the only place where it shows up. So imagine if you do 1D carbon nanotubes and you do a pump probe experiment. So you are basically saying that, look, I shine a pump light and then I shine a probe on top of it and basically do excited state absorption, right? I'm not measuring, they're not measuring excited, I don't do any experiments. These guys are, yeah. The oscillator strength is changing, or there is a new state which wasn't there before is developing over here. So when you increase the intensity, there is a new feature in the spectrum which is showing up, which we believe is because of biexcitons, which is assigned to biexcitons, which wasn't there when you had only in the linear regime. Yeah. Which attractive with each other, which are forming a bound pair. So what happens is you shine light, right? And most of the light, if it were linear, nothing would happen, right? It would just show us a normal spectrum. But I am shining so much light that I actually get some absorption from the excited state to the biexcitonic state. So I have an exciton state and I actually shine, the next photon comes in and that gets absorbed, but it gets absorbed, and when it emits, it emits at, it goes down from there to this one, and that's where basically the biexcitonic state comes out.
Like in a system, you have 2 photons absorbing and 1 coming out.
One coming out, that's correct. That's correct.
And you cannot think of anything else where this would happen.
That's what people assign it to.
For example, if I go to an exciton,
Yeah.
the bound state becomes free and of course
You pay that binding energy, right? You have to pay that binding energy, and in this case, that would be about 2.5 eV. So I have to pay this half a volt of energy to unbind this, which doesn't happen very easily. Yeah. So this is the pump probe experiment in carbon nanotubes, and essentially what you're doing is you shine light, right, and you create excited states, and then you come with the probe beam which shines again on top of this, right? You would absorb on top of this, and what you would see is that while the pump photon is when it's at 1.26, which means I'm sitting at the excitonic, this is the excitonic energy. So I shine light, I have pumped into that excitonic state, and then the next one that comes in, it actually shows, this is differential transmission, just the opposite of absorption. I see a peak or a dip at 1.17. So basically what has happened is the second photon is not being absorbed at the energy of 1.26, but rather at 1.10. That means the two photons, the two excitons formed a bound state, and I'm going from a excited state to a doubly bound state. Yeah.
So is there any selection rule or symmetry criteria which allows those multiple excitement to bind again?
So that's what I'm going to talk about. Not a selection criteria. There should be there's a dipole matrix element which says that this transition can happen with light, but there is also a binding energy that you can actually find out for this stuff. And this shows up in actually also in this context of molecules, right? This is some molecule. I thought it would be okay if I don't say the name of it, nor can I in any case. You shine light, and then you see that as when the light is coming out of the system, initially it comes from this energy, but if you wait a while, it actually comes from a slightly different energy. That there's something that is changing in this molecule, and it comes from a TT state, which is actually a bound excitonic state. And this has to do with the fact that in these molecules, the singlet actually talks to the singlet, which is a single excitonic, the single excitonic state, talks to a biexcitonic state, and they mix together, and that's where the energy gets transferred, and that's where it comes out from. Now you might say, I mean, it's all very good and well, but who cares, right? I mean, why would I care about this? It turns out this has very interesting applications in photovoltaics. So imagine, for the sake of argument, you shine light on a real material, and most of the light, you're looking at silicon, most of the light is, the part of the spectrum, solar spectrum, large part of it comes above the band gap of silicon. So all these electrons and holes that I've created have to thermalize through the band edge, and that's what the energy of my the photovoltaic of the electrons and the holes that I get out, that's the voltage that I'll get out, right? Here all of a sudden I have this state where if I am able to convert this into this TT state, I send in one photon of twice the energy, that gets absorbed, and it breaks into 2 electron hole pairs because I got 2 excitons out, right? And if I am able to harvest these, I get double the current out, right? So that's the reason why people are very interested in this, and they call it singlet fission. Yeah, this happens when the triplet energy is almost 2 times the, singlet energy is almost 2 times the triplet energy. So essentially the idea is, you have, this is the ground state, you shine a photon, it goes here, and that gets converted into this, right? So as they say in Hindi, ek ka do, right?
What happens in the OJ process in atom?
So OJ process, the other should get out, right? It's similar in the sense, correct. It is similar. Actually, it turns out that this energy of this system and this one are more or less degenerate, and therefore they mix, the states mix, and they mix very easily.
What is the kind of interaction between 2 excitons? Is it bipolar?
So that's precisely what I'm going to now get to. That's the interesting. So I hope I have told you why this is an interesting thing to do. So now the question is, how does one go about trying to find the energies of such systems? So of course the standard thing to do would be, okay, you say, okay, look, this is a bound state of 4 particles, 2 electrons and 2 holes. So you write creation operators for 2 electrons and 2 holes above the ground state, and then you come up with a Hamiltonian, and you diagonalize this till you're blue in the face, and you should get the answer, right? The Hamiltonian looks like this. There's no microscopic derivation for this Hamiltonian. Essentially what you say is, this is a very simple way of saying, look, everything talks to everything else with the screen-Coulomb interaction. That's all I'm going to guarantee. Otherwise these are just free quasi-particles. Yeah. So we implemented this in this code called molGW, because we thought, rather than forget about K for a second, this problem is hard enough, as I will show you in a minute. Let's just do this for molecules and see how does this work. It turns out, so there is a TT singlet, and okay, so let me just say, if I have 2 spins, so now I have 4 spins, right? If I have 2 spins, everybody knows you can form a singlet and a triplet, right? But if I have 4 spins, then there are many, the states that I form are 16 states, right? That is the standard way in which you've learnt all the addition of angular momenta and so on and so forth, right? So of which there are 2 singlets that you can form. One is from the triplet, this is 1 cross 1 gives you 2, 1 and 0, the direct sum of 2, 1 and 0, and one of them is also a singlet over here. So you have 2 singlets, one is the S1 singlet and the TT singlet. Okay, don't worry about this for a thing. The only thing I wanted to point out, there is a singlet that you can form out of these 2 triplets. This is what talks to the other one. So when we put all of this together, and there's a screen CISD Hamiltonian that we've written, let me not worry about all of this. Turns out this method works reasonably well. It gives you the energies as you would expect from the best calculations that we could find on the same molecules. We did apples to apples comparison. We get numbers which are pretty close. I mean, good enough for our purpose. But the thing is, this calculation, I mean, what we really want to do is this for solids. And then you start doing a count, and then you realize this is an impossible task, because I have 4 momenta, electron and 2 electron and 2 hole momenta. I will say, okay, look, this is light. I will put a conservation on the momenta. But even so, my biexcitonic Hamiltonian has to be nc square, whereas the n is the number of conduction states that I'm including, nv is the number of valence states, nk is the number of k points that I'm sampling in the Brillouin zone. This Hamiltonian will be a trillion by trillion, right? I don't know about you, but I can't diagonalize a Hamiltonian which is trillion by trillion, right? So what should we do? So what we thought about is, we call these things biexcitons, right? In the way that I was describing these, we really were talking about as 4 particles. We didn't use the fact that these were excitons. So now what we are going to try and do is actually try to use the fact that we have bi-exciton. How much time do I have?
About 5 more minutes.
5 more minutes. Good, excellent. So this is the basic idea. So what we are going to do now is we are going to preform the excitons, right? And then we are going to make them talk to one another. We are not going to say there are 4 particles talking to each other. So excitons have to be built in and bi-excitons have to be built in at the same time. I'm going to preform the excitons. It's like a di-positronium problem, right? I already have 2 positroniums and I'm going to make them talk to each other, right? Why would this change anything, right? The reason why it would change some things is because in a 4 particle basis, both the intra and the interexcitonic interactions are treated together at the same footing. In this, the strong intra-excitonic interaction, which is a monopole-like interaction, right? I have a positive charge and a negative charge. This is a monopole interaction. That has already been built into my basis, right? So now all I am doing is I am accounting for the weaker dipolar interactions between these. This is what is binding these 2 things together, right? So this is exactly the thing as you pointed out. This in principle should not require very many excitons because this interaction is weak. So when I write a direct product state of 2 excitons, I shouldn't need to mix many of them to actually form this bi-excitonic state. And in fact, you can show that this scales fairly well. But then you start asking yourself the following question, right? How do I, I had a Hamiltonian for 4 particle basis. I knew what to do there. But now I have to write about in the exciton product basis, how am I going to write this entire thing down? So there's actually a very nice work by Monique Kombaskat and her group where they have written this theory for composite bosons. So excitons are not really bosons, right? Even though we often think of them as that, they're not really bosons because they are made up of 2 fermions. So it is an effective spin 0 or effective spin 1 particle, right? But it still remembers that it was there were 2 electrons, 1 electron and 1 hole inside it. So what that does is when I bring 2 excitons together, right, all of a sudden this electron and this electron can exchange, right? That is a process. If I once I have formed an exciton over here, I need to make sure that I can account for such things that are happening. This is basically, if I were writing in the 4 particles basis, I have to properly antisymmetrize my wave function. This is essentially all it's taking care of. Similarly, the electrons can also exchange. The holes can exchange, the electrons can exchange. And then of course I have to write an effective interaction between these. Between these 2 I've already accounted for. I already solved the Bezier-Salpeter equation, I bound them together. But now this can talk to this. And you notice here there are equal number of attractive and repulsive interactions, right? Because I have if you count, this is electron, they repulsive, electron and hole attractive, this and this attractive and repulsive. So basically I have equal number of attractive and repulsive interactions. So this is the reason why the effective, there's no monopolar thing, the whole thing is now dipolar, right? Because that's essentially what this is reflecting. So when you do this, we have done this for a molecule and this is for a singlet. This is what happens. So this is, you do the bi-excitonic calculation for the full 4 particle basis. It has 680,000 basis states, right? Takes a long while for us to construct the Hamiltonian, takes a long while for us to diagonalize the Hamiltonian. When you do it in the exciton product basis, right? 3 excitons, I take 3 excitons, right? This is the answer I get. Now, this is pretty good. Right, I mean it's only 5 millieV off, right, or maybe 7 what is it, 6 minus, about 6 millieV off, right? And then I can diagonalize 100 by 500 by 500 Hamiltonian, that's not a problem, right? And you can see that the convergence here is coming out to be pretty rapid, right? This is actually a few excitons can describe this interaction very efficiently, right? So this is basically the idea for using this bi-excitonic basis. We want to do this on a solid, and I showed you a molecule. So this is still work in progress, but we have shown that in principle, if you include everything, the excitonic and the 4 particle, the excitonic basis and the 4 particle give you exactly the same answer, which is the first step. Now, when we increase the k points and truncate, hopefully we can get the same. We can get a converged answer with the bi-excitonic basis much faster. Okay, so In conclusion, I hope I have convinced you that ab initio methods to understand, I have shown you ab initio methods to understand and predict properties of materials. I have shown you that these methods are accurate, reliable and applicable to real materials. We have developed an ab initio method to describe biexcitons in 4 particle and exciton product basis. Both give good answers, but these biexcitonic energies converge much faster in exciton product basis and than in 4 particle basis, and we are implementing this. We have implemented this in solids, and we are in the process of trying to wrap this up. These are the people who actually do the work. I do the talking, right? So Namana is the one who's done all the biexcitonic work. Victor has also been, and Victor and Robin have also been included in this. We have a long time collaboration with HRK, who's been helping us in many of these, and these are the funding agencies. And I thank you for your attention. And
Any questions from anyone, particularly from the students or anyone else?
yeah.
So as far as the biexcitons are concerned, is there any screening for them?
Yeah, so so we have assumed that the interaction between them is just the RPA interaction between the electron and the hole. So we haven't sort of written an effective screening for the biexcitonic Hamiltonian. Is that what you're asking?
Yeah. What I'm trying to understand is if the exciton by itself is a neutral object.
Yes, but it's a dipole.
So it's dipole. So
Yes.
there is when there are dipolar interactions. So this do they get screened?
In principle, yes. In principle, you should be able to write many body perturbation theory for in this and try to, which is what we tried. Which is what actually we didn't do. The Monique Combe-Scott has done. So that's what we have implemented. I think they still think in terms of excitons as the objects, but the screening comes from all the electrons and holes in the system. I think the problem is that there is no microscopic derivation of the Hamiltonian that we are using. So it's a little bit hard for me to say. Clearly they must be, right? But I think it's mostly the electron hole interaction which is screening all of this, at least so far. In principle you could say, look, there are new excitonic states, there should be additional screening which happens because, so that should in principle, but it doesn't seem to matter all that much.
I was wondering whether the excitonic densities themselves behave like some sort of a screening for the.
That is true. So that would be, so what you're saying is a very interesting. So if I increase the density of the excitons to a very large amount, let's say if I wanted to do a BEC with that or a condensate of that, so I pump it really a lot, then I'd have to worry about this aspect as well, because it'll renormalize my electronic band structure, and it'll also give me additional screenings. We haven't accounted for this. This is all still in the not linear but slightly above, but not too far away from that approximation, right?
Manish, I don't think an exciton, the screening would affect this short-range interaction.
So this is dipolar. Yeah. So you're saying because it's dipolar.
Going way beyond the even metallic density.
Yeah. But people, pump very. Experimentalists, hit it with lasers and pump living daylights out of everything. So I don't know. I probably, but that's what we haven't really looked at it very carefully. So yeah, but you may be right. Maybe it doesn't matter all that. Yeah.
If you have a polar system, so does
Yeah.
it then affect, how does it affect?
Yeah, polar systems will have all kinds of other screenings which we have completely, and we took only the electronic screening, right? In all of this, right? I said RPA screening, but there could be lattice screenings as well, and especially at Q as Q tends to 0, there could be long range interactions, as you said, all of that we haven't accounted for. We are just looking at simple non-polar, systems. Yeah.
Can you write a Hartley-like term for this interaction?
A Hartley-like term for the exciton interaction. Yeah, but you see, that's what this is not charged, right? This whole object it's dipole, right? So you'd have to write a Hartley-like term for the dipolar fluid, right? If you wish, right? Probably, I don't know. So interesting. Yeah, we haven't